Referring to is here's our break in real life. We have it down here, right there. I'm sorry, right here is where we pretty much think it is. Now, from here to here, the middle span is where this is your unsupported span. This is your most load deflection, point of deflection would be in the center. Now that's just by gravity, by dead load, period. So we have the bottom deck taking the most of the load here. This one doesn't have any extra, at this point, these pipes aren't on the deck, on the canopy. So the forces are greater on the bottom deck than they are on the canopy at this time. We have C2 times 2 of them. It's one on each side of the node being post-tensioned. And then we have D1 on times 2 on each side of the, well, let's say each side of the truss members, and same thing with C2. Longitudinally, already post-tension. Then they post-tension 2 and number 11. Well, this video will talk about how that limited amount of post-tensioning, and specifically D1 is not the highest rated post-tension member in the series of Ds for this post-tensioning, which I'll get to at the end of this. I think I have 4 videos to do with this. It might stretch out to 5, but if you can imagine that these, since this is not post-tension yet, I'm sorry, it's these are not post-tension yet. The diagonals are not. So we just have 1 and 2 post-tension, and these are just dead weight. They do have connections, concrete connections, but the concrete's weakened shear, weakened tension. So these would just be pretty much under tension at that point. Some of them under compression, but nevertheless weakened tension. So this was the one we understand to be in tension, compression and compression. And with that said, the sag on a typical bridge looks like this from the top canopy and the bottom decking. Imagine my bow, if you will. I'm going to exaggerate, coming from there. Well, I can't get to the end of the structure. It's right there. From there to there. And that's a huge exaggeration down to here also. And that's your sag. Sagging together if the nodes and the plates, truss plates, typically all bonded. This is your weakest point on the joints. This is what keeps this from sagging. All of these joints in the truss plate system, locking it in, making all the truss systems work as one piece. You can't remove one truss plate, or you've just screwed everything. Now, I digressed on truss plates. So to get a crack here, if we move both of these together in unison, imagine both of them moving in unison, because all of these truss plates or nodes, blister bars, all locking in like a truss plate, steel plate. If the bridge were to sag a little bit, we'd have the action of this no longer being plumb on each end because it's sagging in. We'd have a hinged little location on the bottom here where it would rock out, if you will, and you have some clearance at the bottom of this. These cannot, this is concrete, can't deflect. So if you imagine if you were trying to bend this, if this went down just a little bit, you'd get cracking right here inside these joints here and here. We're only going to refer to these 2 joints because we don't have to refer to these. But it would be compressive cracking, and then it would also be coming outwards in the back side here just ever so slightly. So you would have some cracks on the back side of this. As this was still pushing downwards, we'd still have some cracks in here. But we have none. Now, you can prove this. Go to the United Emirates study. They did a concrete truss system. You can find it online, and you can see the images. I shared it in a previous video way back on, I don't know if this channel or my other channel. And they show the cracking there once they loaded it from the center point. So when I'm telling you this, it's got sound theory behind it. Not only logic, but they've already tested a 30-foot span. For clarity, I get a lot of people writing me, they forget where they source their own information from. I source that information, so you don't have to send me the study. I'm the one that put it out there first. It's a United Emirates study. They did a 30-foot test sample. It is not related to this bridge. Many people said they did a 30-foot one, why didn't they do a larger one? They did not do it for this bridge. It was a United Emirates study. There were truss members, roof truss members, and they are actually, here's exaggeration, this is not flat. Theirs were up and down. Okay, there's a huge difference in this whole design. I mean, as far as the configuration, the profile. This, remember, this has to remain flat. So that's also a concern. It has to remain flat for the, well, it can maintain a pitch for the ADA requirements. All right, let's move on from there. But remembering that number 11 and number 2 were post-tensioned after they did the canopy and the lower deck. They did 2, and then they did number 11. They did not. None of these are post-tensioned at this time. This is when the inspector came out. This is when he observed cracks, and 4 over here and 2 here that he identified for us. But he said there are no other cracks similar to those, which implies that there are other cracks. Again, I won't tell you guys everything about my background and everything, but I'll give you a little bit on this. So I did I had to do an FBI requirement class, which says, this is way back in the day, which is everyone wants to tell you the truth. They have to. If you just listen, you'll be able to find it out. Even for example, people that work in the CIA who are supposed to know how to keep a secret, they still got to tell the truth. And how do you get around that? You make them do reports. You can do a report, and you can tell your secrets, if you will. So you have to limit who you tell your secrets to. This person wrote the report and then also told the truth in the report, saying there are no other cracks similar to that, which on their other truss members. He didn't just say there are no other cracks. So that means there are other cracks on these other members. So they suffered, they suffered a moment, a deflection of some type. All right, I'm going to continue this video. Center span, I believe the lower deck, started deflecting downward. That the actual top canopy did not deflect downward, that it had more integrity than the lower deck as far as deflection goes. That pulling downwards created this tension in here. Even though they said, the engineer says that they post tension number 11 and number 2 up here, and I'll give you more on it, that post tension that created tension in here that opened up 4 cracks in this one and 2 in this one. I'm not buying that. I'm not buying that this forces in this direction created a tension crack separation in this one parallel like this. I would say it would be more in this direction, and I would want to see it near here. There are no indications that cracks are up there. This is where the forces would be more concentrated, or even in the middle if you're going to consider that the weakest point of the structure. So I'm not buying that at all. All right, so that's my position on that. Now, the crack here, again, to transport this, they had to, as far as the post-tensioning goes rather, the post-tensioning, even transporting, it should have had the supports in it. We have already talked about it in another video. But over here we have post-tensioning D1 and D2. D1 goes down the middle of this deck. I'll show you in this video the post-tensioning for D1. So you see there's a 471 and I think it's 489. The screen's kind of small for me to read, but those are the kips. Up here at C2 is in the post-tension, is in the canopy, is up there also, but I'm saying significantly the loads are, this has more load on it. If you just imagine this as not being, this bottom canopy, the bottom deck has more load on it by default because it has the canopy, it has the dead weight of the diagonals, and also its own dead weight. All right, so this means it would have more chance of deflecting than this, except for you say, well, they tie them together. Well, I'll get to that too. I'm saying that even though they appear to be tied together, that there's a break that took place, and I think it took place inside the tubes again, in the hollow tubes of the hull, hollow tubes, because we no longer have the supports that are supposed to have been in there, and I think we don't have grouting. Now you can show me grouting. I'll still say that the tubes broke because of the thickness of the cover. So you can show me that. I'm still going with it. Deflection happened here. So let's look at this as a hinge action. We've got opening. We can look at it as he said. It's a separation, and that's his crack monitor. Tension separation, but our forces are coming down this way. And we believe this is the bottom of 11. But remember, we got NTSB and and everyone's showing that this is located in the wrong position with an arrow. So it's purposely being, I'm going to use my man's statement again, whitewashed. All right, because it works so many ways in this one because of the whitewash, literally, and whitewash. Just notice that's open. That's not compressive. That means that forces aren't, and they're in line with each other. They're not passing each other. So if the tension was doing this crack, it would create a shear here, and these would not line up like that. There's a slight shear here, I would say, that shows that it's movement there, but this is higher up, and we have an arch. Arch has that effect of doing that. Here we can see that these would all line up pretty good back into play. But now we see that this one, what do you notice here? That this is higher than this. They're not in plane with each other. It's a photograph, so we can discount the photograph thing. Remember, I have to add my photography skills and say that we have some distortion. You guys find this, I'd love it. There's a sky in the background. There's the banners, orange railing maybe. This is not down at number 2. I did not find it down there at number 1 and number 2 connection in the images. I don't know where this is. This elevation was taken. This would show that's deflection, if you will. If we can find out where this is actually located, this image in real world. It says photo 5. So if you follow this crack, the top is wider than the bottom. It's tighter here and wider at the bottom. This gives us, if you imagine the bottom of the bridge this way, and if you deflect it in the middle and come back up again, real exaggerated deflection, you would get cracking on both ends, 11 and 11-12 node and 11-12 connection and 1-2 connection. And the pulling downwards, if you could, typically a bridge will deflect, the top and bottom cords will deflect in unison. This did not, but I'm saying we don't have a compression. We have separation, and as he said, tensile forces. So now we have the forms are not present at this point, which they're supposed to be during this post-tensioning. They were not scheduled to be removed until the bridge was in place. Right there, you'd have to show me, well, 2 things. I want to say that they're not being forthcoming with the plan still. They're not showing all the addendums. They just want to see what we can get by. And ultimately, they're going to win because, they're going to publish it. It's going to get more traction than any of my trash videos or anyone else's comments. Everyone else will go down the conspiracy hole, including myself. So now we have this rod here that's supposed to have been tensioned. More cracks. He doesn't address that this longitudinal post-tension rods that are inside here are causing cracks. He's addressing this one. With that said, if this bridge was deflects from the center now, if you guys can imagine a bow, if you will, deflection in the center, you would create a force on that rod that if this is a pencil, the forces would be pulling downward. So you're going to get a crack here. Going both directions actually, right? You got counter forces. So that could give you the mirror crack coming through. I'm saying this is rebar reinforcement, also representing movement. This is an open, this is a tensile break. This is an open crack. Insignificant if you like, but you have to add these cracks up. Take a little bit of liberty here. This is a United Emirates study, so I'm going to just give you guys a general idea. We know they have, which I'll give away a little scene stealer. Later on, I'm going to talk to you about how number 10 actually has 4 post-tension bars in it, not 2. And they're roughly configured like this, 1, 2, 3, 4. And number 11 has 2 coming in this direction. If we could use this study for a bit and visualize bars coming through, that their node does not look like this, and they don't have this upright. But we have the number 11 come in this direction. If we could visualize 2 of them, 2 bars, going through the middle of this, about 1 foot 1 inch apart from here to here, the engineer, the BPA, says that when they were loading number 11, post-tensioning number 11, that it created temporary forces onto the steel, is what his words are. Steel, not the post-tension rod. Let's say there's the post-tension rods. 1, 2, 3, 4. We don't know what the steel looks like, but we have a rough idea that it's sort of like this, the cage, if you will. And he's stating that the cracks are not this direction per his reported mentioning of like 70 inches, 126, whatever it may be. He didn't say 126 and then at the far end, 120, which indicates it's like on a diagonal. The cracks would be in line with this. As you can see, these are not horizontal. When this is in its diagonal position, these also are diagonal. All the reinforcement is cracks. He's implying that the forces coming in this direction created horizontal cracks from the steel, but there is no horizontal steel in that setup, the cracking. So this is the United Emirates study, and this is the way they've configured it, and they use these plates up here to lock everything in. Yet they still came up with an issue, and they're showing you. It's a beautiful study. I won't trouble you with it. Isn't that interesting? Lowe's. 30-foot long model. They did a lot of things on it. Bear with my vision here. They're showing you how they poured it. I mean, they really disclosed a lot of data on the truss. The ultimate truss, I think, were 165 feet. Hey, cat. He's showing how he had a problem getting off the formwork even, using sawzalls, etc. It's a long study to read. They used a different configuration. They even showed how the forms floated on them when they put the concrete in there and gave deformation of the concrete. You can see it's wider here and at that point also. And that's from the formwork using the styrofoam. See the different shapes. Kind of weird, right? Because clearly that looks larger than the other one and the form is in place. So if you read the study, they said that this floated, etc. Well, I don't buy that because I see foam on each corner. Floating says it's repositioned. I don't see a reposition here. I see just a bad shape. When we know concrete should not be used in a flexural position. I just find this ridiculous. So here's the loading of the 30-foot member. It may appear to be small, but apparently this is 30 feet in length. We're going to see cracking, and it's a different design, as you can see. Take note, I don't know if I said in the other video, but take note, they do have some bars here to act as another truss member. They just, negated the concrete at that point. And we're going to slide up, and we're going to show you, well, there's the consistently plate, the forces they're showing. And they're showing it again. These are all the load monitors. We're going to show the deflection, etc. And well, let's just jump right to the cracking now. So at loading, the deflection, the load being in the center of the span, which where the greatest loads are on unsupported spans, they show the cracking taking place here and here. This has a different form than the R bridge, than the FIU bridge. Now they released it at this point. They did not show the photographs with it still at the point of failure. These are the photographs after failure. So in other words, this is the releasing of the load, and now we're back at what looks like when the load comes off of it. And if you take note, you've got an open joint now. So during compression, it cracked. And then when they let off the load and all the tension on here returned it back to its form, it then exhibits itself in this format. And there we have it again. Okay, at 200 kips, the cracking had affected all the sharp angles connected, especially at the web diagonals interfaces. Sharp angles. This is where they determined that they should make them round. Going back to this, these are the sharp angles. This is what they're saying. They're blaming it on sharp angles. I just think that's Just wrong thinking, but heck, this study's sharing data. Now, would you consider that a sharp angle in number 2? Correction. Would you consider that a sharp angle in number 11 and where it meets the deck? If you have the crack here, we have that piece of section here, right? And then we have the crack continuing down through it. Would you see now that that crack would be continuing down upon loading? But we have no loading at this point besides dead weight. So now you can see why I've calling it deflection from the center by dead weight, because obviously they weren't load testing it with a machine like this. And you'll be surprised, there are some huge machines that you can load test things in the field. You set it up and it can happen. Okay, so that's the end of this video. Here's your monitors. There's more cracking. As you can see, it's at the base. Middle vertical cracking. We really need to see all the cracking of the structure. That's the one I wanted to show you. This is that continuation of cracking. Remember, we had it up here with our structure, and it continues down like this. Our deck is flat. These are truss members, so we don't get to visualize if this went through the deck, because we don't. Obviously, this is it's a deck. The deck is huge. It's 30 feet wide. In theory, you would think that that crack continued through the deck